Alright, a quick test to make sure you can actually hear me talking. Let me know if you can hear me right now. I'm using the webcam, using the microphone on there because my headset microphone, there's sort of a ground loop because my Surface tablet doesn't have a grounded plug, and then you get this annoying hum. Uh, this seems to have better audio, so we'll go with that. There's sort of a ground loop. All right. I hope everyone's staying healthy so far. Teaching center's talking to me. We'll close that for now. We don't need that up. Here, while we're waiting, you can see the bizarre thing that happens if I use my screen recording software to actually show the screen itself. You get a fun. Oh, look at that. That's exciting. Whoa. Okay, back to here. All right. So I'll try to collect some more information from everyone over the weekend to figure out how this will all work. We might try to do Zoom meetings once or twice a week so that you can all actually talk to me over voice. Right now all you can do is text. That's the one downside of doing YouTube rather than Zoom. The upside with the YouTube is it's going to save it automatically onto my YouTube channel, so people that can't attend live, they can watch later. Zoom lets us record, but apparently a lot of people are having a lot of trouble with recording their meetings on Zoom. So we'll try this, we'll see how it goes. Most of you indicated in my survey that you're happy to just go ahead and ask me questions over here on Piazza. So I've got Piazza open as well. I'll try to just answer the questions in the YouTube chat. Feel free to, if you have some last minute things you want to see in this hour, feel free to throw them in the chat and I'll try to sneak them in as we go. Alright. Where are we at? 1 minute. 1 minute until we begin. Let me see, does this thing have full screen mode? It does. Let's go full screen. Alright. Oh, that pen's a little bit thick. I don't like the 2-point pens. We'll live with it. We'll do a 1. Maybe a bit better. Okay. All right. Okay. I do have one error example coming up. See that request from Sarah there. So my clock says it's 10:30, so we might as well get started. Hopefully everyone was trying my warm-up problems, and we'll dive right in. So, first bit here, geometric series formula, right? That's just straight up geometric series. We're just replacing x by r, so there's nothing fancy there. Now the point of the first one is that you can take the derivative of both sides of that equation, and when you take the derivative of the power series, right? When you take the derivative of the left-hand side, what are you going to get? You're going to get the sum. Oh, that's really bad. I don't know why it's so fat now. Let's go with that 1 point pen. Okay, so on the left you get the sum n going from 1 to infinity of n x to the n minus 1 when you take the derivative. And if we want to, we can also re-index that, so that's going to be equal to the sum n going from 0 to infinity n plus 1 x to the n, right? So if we drop the beginning index by 1, right, we drop that by 1, then we have to increase everything else by 1 to compensate. And when we take the derivative of the other side, right, the 1 over x minus 1, well, that's just 1 minus x to the minus 1. And if you take the derivative of that, well, you're going to get minus 1 minus x to the minus 2, and then times minus 1, because chain rule. So you just get, I'm going to update my pens before the next time I do this, you're going to get 1 over 1 minus x squared. Okay? And so if you take the derivative again, one more time, taking the derivative again, take the derivative of this and of this, then you're going to get sum n going from 1 to infinity n plus 1 times n x to the n minus 1, and that's going to be equal to 2, where did my 2 go? 2 over 1 minus x cubed, using the same logic for the derivative that we used for the first derivative, right? That's 1 minus x to the minus 2. Minus 2 comes down. There's another minus sign from the chain rule. And so now if you've got that x to the 4 there that you want to account for. So we just have to multiply both sides by x to the 4 and maybe do a bit of re-indexing. So what we get is the sum, n going from 0 to infinity, n plus 2 times n plus 1, x to the n. And on the other side, I've still got 2 over 1 minus x cubed. Okay, so I want x to the 4 over 1 minus x cubed. So first thing I got to do is I got to divide this by 2. That'll get rid of the 2 over there. And then I want x to the 4. So I got to multiply both sides by x to the 4. And so that plus 4 right there just comes because we multiply by x to the 4. Okay, so that's the first warm-up problem. This is pretty typical manipulation of power series. You start with a known power series, you take derivatives or you take integrals, you shift an index, sometimes you got to multiply by a power of x, things like that. You can also substitute. We can do these kinds of tricks. Okay. So hopefully that came through for you all and that was reasonable. Let me know if it's not. I'm going to see if I can remember how to save my pen. Oh well, I'll set it up later. I used to use the 2-point pens and they were just fine, and I don't know why it's not good anymore. But anyway, we'll live with it. Okay. So on to the next warm-up problem. Feel free to shout at me in the chat if you see something that you don't like. So we want a power series whose interval of convergence is 0 to 6. All right. So the center of that interval is 3. The radius of the interval is also 3, right? 3 minus 3, 3 plus 3. And so that tells me that I'm looking for something that is going to look like x minus 3 to the n. The way I get a radius of 3, the easiest way to get a radius of 3 is just put a 3 to the n on the bottom, right? Because then if I think of this whole thing here, right, I think of that whole bit as my r in a geometric series. I need r to be less than 1, so if this thing is less than 1, that means that x minus 3 has to be less than 3 in absolute value. Okay, the trouble is that this power series here, that's going to converge on the open interval from 0 to 6. I need to include the right endpoint. So how do I include the right endpoint? Well, the way I get the right endpoint in there is I want to set things up so I've got a convergent alternating series when I plug in x is equal to 6. So if I put in x equal to 6, I get 3 to the n over 3 to the n. So right now I just have a 1. So that's so far not good enough. But what I can do, well, first of all, let's put in that minus 1 to the n. Okay, that makes it alternating. But that's not a convergent alternating series. I need the terms to go to 0 as n goes to infinity. So I can do that if I just put an n in there. Okay, that's going to do the job. Because now if I put in x is equal to 6, right, that right endpoint, I get minus 1 to the n over n. That's an alternating harmonic series, so it converges. All right. Now, should we try to squeeze the third one in on this slide? I can always add a new page if I need to add a new page. But let me see. What does this one do? Add current. Oh, I can. There we go. That's how I do it. Okay, I've got my pen. Good. It's been a while since I used this app. This is how I used to do my videos before we built the light board. Let me do the next one over on the next page. So let me add a page here. Okay, I just have to remember, how do I add a page? Insert a new page. There we go. Good. Okay. So let's do that integral. So we want to do this. We want to do the integral from 0 to 2 of e to the x cubed dx. How are we going to tackle that? Well, first of all, we need the Taylor series for e to the x. So e to the x, Taylor series looks like this. Sum n going from 0 to infinity, x to the n over n factorial. Okay? And so to get a Taylor series for e to the x cubed, all I have to do is actually substitute x cubed on both sides of this equation. So e to the x cubed will be the sum, n going from 0 to infinity, of x cubed to the n over n factorial. And I can write that as the sum, n going from 0 to infinity, of x to the 3n over n factorial. Okay? Alright, so there's my Taylor series. So now let's do the antiderivative, right? So we want to do the integral of e to the x cubed dx. And so we can say, well, that is the integral of the sum, n going from 0 to infinity, x to the 3n, n factorial dx. And the whole point here is that we can exchange the integral and the sum. Right, so this is allowed, not something that we proved, but, well, we'll live with that. So we just have to do this integral, x to the 3n dx. And that's just power rule, right? And so power rule is easy enough. We're going to get the sum, n going from 0 to infinity, 1 over n factorial times x to the 3n plus 1 over 3n plus 1. Okay? Plus c, I guess, if you want to put your, okay, fine. Here's plus c. Now you want to put the limits in. All right? So we're going to go 0 to 2 e to the x cubed. Well, we simply take this antiderivative, we evaluate it at the two endpoints. Okay? So when x is equal to 2, we're going to get the sum, n going from 0 to infinity, of 2 to the 3n plus 1 over n factorial times 3n plus 1. And I guess technically we need to subtract off the lower limit, the constant term. But you know, the constant is there on both, right? So it cancels out. And that's the result. Okay. So we'll move right along. It's a little bit weird doing it this way because none of you get to shout at me. You can type at me if you want. We'll see how it goes. Hey, I see I've got about half the class in there. Awesome. Thanks, guys, for showing up. We can also talk about, you know, what's reasonable in terms of timing for this. We might have to adjust the timing. We'll see how that goes. Let me move that out of the way. I got to work on my rendering. Sorry, this is that's f prime right there, f prime of c. Okay. I threw in a couple of slides here. I don't want to spend any time on these because we want to get done in an hour, right? I got to go make lunch for my kids. But we did these in class last week. I just wanted to remind you that Taylor series comes from Taylor polynomials, right? So back in Calc 1, you look at polynomial approximations to functions. You have this Taylor polynomial formula, right? So the coefficients in the Taylor polynomial you get by computing successive derivatives of your function. You plug in this number c, you divide by k factorial. Those give you the coefficients, right? And then you just put together the polynomial. And for some functions, sometimes it's hard to notice patterns. You just keep taking derivatives and plugging in numbers, and you know, hopefully you were only asked to do like up to degree 4 or something, so you just take the first 4 derivatives, you plug in the numbers, right? If you want to get to Taylor's series, well, you want a formula for the coefficients. So typically you have to take enough derivatives that you can see some sort of pattern, and then you write down the general formula, right? And so the point of moving from the Taylor polynomial to the Taylor series is, well, when you study Taylor polynomials, you realize that your approximation improves as the degree increases, and you say, well, why not just let the degree go to infinity, right? So if you let the degree go to infinity, you don't really have a polynomial anymore. Now you have a power series. That's kind of why we introduced power series in the first place, right? So then you get to this. And then, you know, what you would like to be able to do is you would like to be able to say that this is equal to f of x, right? And for the purposes of Calc 2, assume that you can always write down that equals sign as long as you're within radius of convergence. Sometimes the radius of convergence for the power series gives you an interval of convergence that is smaller than the domain for the original function, and then you only have equality on that interval of convergence. But we live with that, right? And we won't worry too much about the technical details. Technical details more or less come down to this Lagrange formula. So the Lagrange, this Rn is the difference between the original function and the Taylor polynomial. You can show that for most functions we deal with, if you take the limit of this thing as n goes to infinity, you get 0 as long as you stay within the radius of convergence. Okay, so that's essentially why we can equate a function to the power series, right, the Taylor series, because you have this equality is true, and this will be valid for any n. And so as long as that remainder goes to 0, then in the limit we get the equality of the function and the Taylor series. All right, so that is the kind of standard game that we're playing here. Okay, moving on. Again, feel free to chime in the comments if you have questions, comments, or concerns. Here are some basic examples. I think we tackled some of these in class last week. We already used the one for e to the x, right? So the point for the first one is that, well, you know, f prime of x is e to the x, f double prime of x is e to the x, and so on, right? All the derivatives are e to the x. So f of 0 is 1, f prime of 0 is 1, f double prime of 0 is 1. And so when you plug things into the Taylor series formula, which says that you should do the nth derivative at 0, right? We're evaluating at 0 over n factorial x to the n. Well, all those derivatives are just 1. So you get this formula that we were using. 0. We get the formula we were using before, x to the n factorial, right? Cosine, similar game, right? We know that, oops, sorry, my hand bumped the thing. Cosine of 0 is 1, right? The first derivative is minus sine of 0 is 0. Second derivative is minus cos, which is minus 1, right? And then the next derivative we get sine, which is 0. And then we take one more derivative, right? So we're on to the first, second, third, fourth derivative. we get back to cosine, right? And then the pattern is going to repeat, right? We always cycle in this 4, right? It's 1, 0, minus 1, 0, 1, 0, minus 1, 0. We're going to keep repeating that cycle. So again, you plug things into the formula, and so you can do this in a few steps, but essentially what you want to do is you want to indicate a couple of things. One is that only even degree terms are going to go, right? 0, 2, so here's, this is 0, 2, 4, right? So only the even degree terms show up, and one of the ways you do that is you just say, okay, I have x to the 2n, right? Only the even degree terms, right? And then you have that 2n factorial, right? X to the 2n over 2n factorial, because we always divide by the same factorial. And then, well, we noticed that the signs alternate, right? So 0 is 2 times 0. 2 is 2 times 1. 4 is 2 times 2. So where 0, 1, 2, that's your n, right? So we have plus 1 when n is even, minus 1 when n is odd. So we need a minus 1 to the n. Okay. All right, let's do that natural log. So again, there are some tricks for doing the natural log, but let me point out if you wanted to do it directly. Oh, by the way, interval of convergence. Both of these, interval of convergence is all real numbers. Okay, easy to check that using the ratio test. You do the ratio test, you're going to get basically x to the n plus 1 divided by n plus 1. N goes to infinity, you get 0, so we're less than 1 for all values of x. For the natural log, we can actually just work directly from the formula, right? So we can say, well, look, log of 0 is 0. We take the first derivative, right? So we get h prime of x is 1 over x. H prime of oh, sorry, not log of 0, log of 1. H prime of 1 is 1, right? Second derivative, we get minus 1 over x squared. H double prime of 1 is minus 1, right? Third derivative, we get 2 over x cubed. So h triple prime at 1 is 2. We'll do one more. So we get minus 2 times 3 over x to the 4. Fourth derivative at 1 is minus 2 times 3. And you might guess that from here you're going to get sort of a factorial pattern, right? So the nth derivative at 1 is going to be, so again we need a sign factor. Let me see. We are positive when n is odd, right? And negative when n is even. So we need an n plus 1. And then we have, let's see, h to the 4 is 3 factorial, right? The third derivative 2 factorial. So we actually have n minus 1 factorial there. And then of course you want to divide by n factorial. Divide by n factorial. And n factorial is just n times n minus 1 factorial. So we can actually simplify this to just minus 1 to the n plus 1 over n. And so that means that your power series is going to look like this. Sum n going from 1 to infinity minus 1 to the n plus 1. This time it's x minus 1 to the n because we're centering at 1, and then divided by n. And this time radius of convergence is just going to be 1, right? Interval of convergence, let's see. So the interval of so this, we know that we're good to go, kind of the interval is 0 to 2, right? We're centered at 1, radius is 1. And if we plug in x equals 0, we have, let's see, we will not get an alternating series at 0, right? Because that will be a minus 1 to the n plus 1, that'll be a minus 1 to the n. But that makes sense. We expect it to diverge to minus infinity at 0 because the natural log diverges to infinity at 0, or minus infinity at 0. At the other endpoint, though, when x is equal to 2, we do have an alternating series there, right? And when x is equal to 2, we get 2 minus 1 to the n. Okay? So we actually get, that's just going to be 1 to the n. So we get an alternating series, right? We get 0 to 2. And notice that at 2, you essentially just have the alternating harmonic series. You'll remember I mentioned that the alternating harmonic series adds up to log of 2. Well, that's where you get it. Okay. Oh, I see I've got a question from Hannah. Yeah, so Hannah's asking if we actually have to prove. Well, yeah, let's say, I mean, I might ask you to derive one of these, right? I mean, you're getting a take-home test, so I got to make you do a little bit of work. Also, I guess you don't, Hannah asked about memorizing. You don't have to worry about memorizing anymore because everything's open book from here on out, right? It's all take-home exams. And so, yeah, I might ask you to derive one of these from first principles. But for most problems, you just look up the Taylor series and you use it, right? I'm gonna answer over here on the text. All right, there we go. Just in case people are tuning in later, I don't know if that chat log shows up for people that are watching later, but now it's there for posterity if it does show up. Okay, moving along. Oh, I think I skipped a slide. Here we are. Let me make sure I didn't go too far. Yeah, just one. All right, so manipulating power series. This is where most people need the most practice. Once you get used to it, though, it's pretty straightforward. So you can play around. You can add, you can multiply, you can divide. And of course, a power series for a polynomial is just the polynomial, right? Because all the higher order derivatives are just 0, and so if you try to take the Taylor series of a polynomial, you just get the polynomial. And in particular, that's going to be true if you've got just a power function, right? The Taylor series for x cubed is x cubed. Okay. So the way you would do something like this first one, you can do this one right here on the slide actually. We just say, okay, we have x cubed. 1 over 1 minus x, right? That's geometric series. So we can just say, oh, that's x cubed times the sum, n going from 0 to infinity, x to the n. And you can bring the x cubed in. We can write that as x to the n plus 3. So that's all you got to do for something like that. Okay. For something like sine x over e to the x, well, first thing I might do, because we can do division, but division is kind of hard. You've got to do long division. There's a post on the forum about that Sarah asked for. So we've got sine x e to the minus x. If we rewrite it like that, we don't have to worry about dividing, we can just multiply. So then we say, okay, so sine x is, and I could give you, you know what, it's not going to come up. You can write down sort of general formulas for what does the nth term in a product of power series look like. You can do this, but generally what we do is they say, so sine x looks like x minus x cubed over 3 factorial, x to the 5 over 5 factorial, and so on. And then for e to the minus x, well, basically we know that if e to the x is the sum x to the n over n factorial, then e to the minus x will just be the sum, it'll just be minus x to the n, and you can factor out that minus 1. So minus 1 to the n times x to the n is the same as minus x to the n, right? So now you just get an alternating sign for e to the minus x. So you get 1 minus x plus x squared over 2 factorial, and so on. And then you just multiply out and you collect terms, and it's kind of tedious, and hopefully you don't have to do a lot with it. But if you only need the first few terms, then this is probably what you want to do. You want to just sort of write it all out like that. And so you'd go x, you just FOIL. So we go x, here I'll use this thing. We go x times 1, x times minus x, x times x squared over 2, right? And then you move on and you do x cubed over 3 factorial times 1 times minus x times x squared over 2. And you just multiply it all out and collect terms, right? And you try to be on the lookout for when are you going to get two terms with the same power, right? So for example, for x cubed, there's going to be an x cubed times 1 showing up there, and then also x times x squared, right? So you might have more than one term that contributes to that particular coefficient. So you have to watch out for that, but that's basically it. In general, you can sort of work out, like if you have an x to the n, and you multiply by bn x to the n, you multiply that out and you get a series that looks like cn x to the n. And the formula for this cn, it's actually, you can actually write it out as a sum. It's like a sum k going from 0 to n. Sorry, that was a really bad n. Writing on a tablet is tricky. And it would look like a k b n minus k. You would get something that looks like that. So you can write down a general formula for a product of power series, but it's messy. And if you look at the examples in the textbook, it only ever asks for kind of, give the first few terms. So that's probably, to be fair, that's what I'd ask for too, right? Now, I'm going to do sine x cubed here. Secant I'm going to do on our new page, because that one actually takes a bit of work. But for sine of x cubed, we can just do this. We just say, okay, look, sine x, right? We set up here, what is sine x? Right? This is the sum. The general, what this looks like is the sum. N going from 0 to infinity, minus 1 to the n, x to the 2n plus 1, over 2n plus 1 factorial. So if I want sine of x cubed, all I have to do is I just take x here, and here's x here, right? So those match. I just have to replace that by x cubed, right? And so then I kind of maybe on the side I say, well, look, x cubed to the 2n plus 1, I multiply the exponents, that's going to be x to the 6n plus 3. And you just substitute it in. So this would be the sum, n going from 0 to infinity, minus 1 to the n, x to the 6n plus 3. But still 2n plus 1 factorial, right? We're changing x, we're not changing anything else in the series. So we get to that. Okay, and now, secant. I threw this one in just to give you a bit of a challenge. What do you do with secant? Let's think about it. Okay, I need a new page. Let me see, where am I? I'm here. Insert a new page. Go. Nope, 1. There. Alright. So, what do I do with secant x? Well, secant is 1 over cos. Okay? And I also know that cos x is going to be the sum, n going from 0 to infinity, minus 1 to the n, x to the 2n, over 2n factorial. So how do I get secant? Well, I'll give you the first few terms. It's kind of writing out a general formula here is going to be a challenge, but what we do is we do this. We say, okay, here is the series for cos, 1, minus x squared over 2 factorial, plus x to the 4 over 4 factorial, minus x to the 6 over 6 factorial, right? And I'm dividing that into 1, right? 1 divided by that. So we do this. Divide into 1. And so we say, okay, 1 goes into 1 how many times? 1 goes into 1 once. Okay? And now we take that number and we multiply by all of this and we put it here. So we get 1 minus x squared over 2 factorial plus x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and we imagine that that goes on forever. And we subtract. Okay, so 1 minus 1, those go away. And we can think of this as, this is like 0x squared plus 0x to the 4 and so on. So minus x squared over 2, we get x squared over 2 factorial minus x to the 4 over 4 factorial plus x to the 6 over 6 factorial and so on. And now we come back and we always look, we're always looking here, we're always looking at that leading term. And we say, okay, how many times does a 1 go into x squared over 2 factorial? Well, 1 times x squared over 2 factorial gives me x squared over 2 factorial. And now I got to take the x squared over 2 factorial and multiply by this, and I put it here. So I get x squared over 2 factorial. Then I'm going to get minus x to the 4 over 2 factorial squared. And then I'm going to get plus x to the 6 over 2 factorial 4 factorial. That x to the 6 comes from x squared times x to the 4, right? And we could do the next one as well, but let's not get carried away. And we subtract. And so now I've got to do, for x to the 4 over 4 factorial, I'm doing this, right? I'm doing, it's minus 1 over 4 factorial minus minus, so plus 1 over 2 factorial 2 factorial. And you think about how you want to simplify that. I guess we could write that as minus 1 over 4 times 3 times 2 factorial, 1 over 2 factorial, 2 factorial. So we get 1, 2 factorial, and then we have 1 1/2 minus 4 times 3 is a 12th, right? So 1/2 is 6 over 12, so I get 1 over 2 factorial times 5 over 12. And actually that 12 is 3 times 4, so if I want to, I can write that as 5 over 4 factorial. Sometimes you just got to play around and try to figure out what's the right simplifying that I want to do, because sometimes you're going to notice patterns, but not always. So f5x to the 4 over 4 factorial, and we subtract. Okay, you know what? I'm going to skip that one because I just wanted to get the first few terms, and I've got enough to get the next term, right? And now I do 1 divided into here, and so I'm going to get 5 over 4 factorial. Do a little bit better job of writing that. I deleted my thing. 5, 4 factorial, x to the 4, and you could keep that process going as long as you want, right? So division with power series is a pain, but I mean it's mechanically straightforward. You can do it, and of course you can program a computer to do it as well. So that you don't have to sit here and mess around with fractions. You might need the human to kind of play around with those fractions and see if you actually get any kind of pattern out of them, but the computer can help with the calculations. Alright, I don't see anyone complaining in the comments, so I'm going to move right along. You can always pause this and come back later if you need to. That's the nice thing about putting it up on YouTube. Okay, binomial series. I'm not going to say too much on this because I did a bunch of videos and put them in the book that cover kind of all the basics. So you can go take a look at those if you need a refresher on how some of this goes. But you get something that looks an awful lot like the binomial formula, right? If this alpha is an integer, there's that binomial formula with Pascal's triangle, right? And these are just n choose k kind of coefficients. But you can actually make sense of binomial coefficients when n is not an integer. And the interesting thing is that if n is an integer, once you get to n plus 1, this term is 0, and then all the coefficients beyond that are 0. But if you have this alpha, which is not an integer, you actually keep going forever, and you get a series. Okay. So the book mentions that the radius of convergence for binomial series is 1. You see that here. Okay. Sometimes you can include an endpoint, sometimes not. The book mentions that understanding when you can and can't do that is kind of tricky, so we'll just sort of sweep it under the rug. All right. But I just want to point out, once you have the binomial formula, how do you use it to do Taylor series? And again, maybe we don't try to be too general here. I mean, we can write it down what it looks like. But 1 plus 2x is, of course, that's 1 plus, we're going to think of that 2x as a single piece here, because that 2x is going to replace x in the binomial series. And the power is 1/2, right? So that 1/2, that's our, this is alpha in this case. Okay. All right. So we can basically just put things in. We can say, all right, so this is going to be, it's the sum, k going from 0 to infinity, of 1/2 choose k, and then 2x to the k, right? And that's pretty much it. We can just write it like that. Now, you might not be satisfied with those binomial coefficients because you don't actually know what they are. And so you can work out what a few of the first ones are just to kind of get the hang of it, right? So 1/2 choose 0. So by definition, when k is equal to 0, that's always by definition just 1. So the first term, we just get a 1. 1/2 choose 1 is a half. 1/2 choose 2 is going to be a half times a half minus 1, which is minus a half, over 2 factorial. So you get minus 1 over 8. And it just kind of gets messier from there, right? So the next one, 1/2 choose 3, you're going to have a half times minus a half times minus 3 halves. You divide by 3 factorial. It gets messy in a hurry, right? So typically we just sort of live with that. And it's nice to have this series, but again, where this really comes in handy is maybe not necessarily for writing out the entire Taylor series, but you want to approximate, the value of some square root when x is close to 0. Well, maybe you only need the first few terms for that. Going on to the second one. So this one here, well, that's 1 plus x squared to the minus 2. Sorry, that 1 plus looks like a 4. So in this case, alpha is minus 2. Okay, alpha is minus 2, and we're replacing, with the x up here gets replaced by x squared. But again, you can just replace that in the power series. So what you're going to get is the sum, k going from 0 to infinity, of minus 2 choose k, and then we have x squared to the k, so x to the 2k. And this time you maybe want to manipulate a little bit more, because what does minus 2 choose k actually look like, right? You can probably mess around, and also you don't need to use the binomial series for this, right? We actually worked out, like in the warm-up, one of the things we saw in the warm-up was how to get taking derivatives of geometric series. We know that this looks like a sum, n going from 0 to infinity, of, what's it going to be? It's going to be minus 1 to the n times n plus 1 times x to the n, right? We can derive that by taking the derivative of the geometric series formula. Oh, maybe I might need another minus sign in there. Go back and check. I'm not going to rederive it. And then you can just plug in x, replace x by x squared, and that becomes x to the 2n. So then, comparing the two, you think, well, maybe this minus 2 choose k should end up looking something like this. And if you want to kind of reconcile your two answers, then you start playing around to see what you get, right? And so you say, okay, minus 2 choose k, what is it going to look like? Minus 2 choose k. Well, the first one is always just 1, right? Then we get minus 2. And then the next one is going to be minus 2 times minus 3. So I get 6. And then I get minus 2 right? So I'll have minus 2, minus 3. The next one I subtract 2 will be minus 4, right? So I get minus 2 times minus 3 times minus 4. Right, I get minus 24. Actually, these are just, there's an alternating sign, but these are also just factorials, right? So actually what we get here is minus 1 to the k times k factorial, right? And so you can, again, this is how you can kind of match them up and you can reconcile. So if you were to plug that in, you can get things to match and see that you get the same result either way. Okay, how we doing? We're getting there. 7 slides to go. We're almost through the end of the Taylor polynomial stuff, and then I got a couple differential equations I'm going to do for you. What do we got? About 20 minutes? I think we're doing all right. I'm not seeing anything in the chat log, so let's jump. Okay, don't worry about this slide. It's just for fun. But as you move on, those of you who are going to do like physics and engineering, you're going to run across creatures like this, Bessel functions. Bessel functions show up in a lot of kind of mechanics problems. You're trying to solve things like vibrations of a drum head, things like that. You find that these Bessel functions, they make appearances. And the way you end up with these things is essentially by solving differential equations. I mentioned we're not going to do a lot with it if this is something you do in a differential equations course, but you can do power series solutions to differential equations. So you assume that y is a power series, you plug it into the differential equation, you kind of put everything in, you have to do a lot of stuff with shifting indices and moving stuff around. But typically you get some sort of recursion formula for the coefficients in the power series, and you try to look for patterns and figure it out. And that's how you end up with these things like Bessel functions. So these do show up. They have a lot of applications in other areas of engineering and physics. And there is no other way to define these except using power series. So if you do move on, you'll run into things like this, right? So this is why we care about power series and Taylor series, is that not only can we represent existing functions using power series, but we can create new functions using power series. And this is a very useful thing to be able to do. Okay, another thing you can do, you can evaluate limits. Now, you might argue that this isn't really anything new or exciting because you already know how to do these limits using L'Hopital's rule. Fair enough. Fair enough. You know how to do them using L'Hopital's rule. But it's a fun game that you can play. You can say, well, look, this is the limit, x going to 0. If I plug in the power series for cos, I get 1 minus x squared. Oh, this should be, sorry. I probably should have done that. Sorry, slides were done in a hurry. 1 minus x squared over 2 factorial, x to the 4 over 4 factorial, and so on. And then I subtract off 1 and x squared over 2. And we have x to the 4. And so, of course, the 1's cancel, and the x squareds cancel. And then we divide everything that's left by x to the 4. And so you get a limit as x goes to 0 of 1 over x to the 4 times x to the 4 over 4 factorial minus x to the 6 over 6 factorial, and so on. And divide by x to the 4, so that's just a 1. That's a 2. But everything else except for that leading term still has an x in it, right? So you just have 1 over x to the 4 when we cancel with that x to the 4 out front. X goes to 0, so all the other stuff goes to 0, and we just get 1 over 4 factorial, or 1 over 24 if you want to write it like that. Similarly, for the next one, we can say that, well, using binomial series, square root of 1 plus x is going to be 1 plus 1/2 x minus 1 over 8 x squared, and so on. I didn't memorize that, it's just that we did it like a slide ago and I've remembered it that long. Okay, and so we if we subtract off 1 and minus 1 and minus a half x, right? We put that in. Well, then we're going to get minus 1 over 8x squared plus some other stuff. We divide by x squared, and so we expect that the limit in this case should be minus 1 over 8. And again, if you want to, you can use L'Hopital's rule. You're going to need it a couple of times. But if you do L'Hopital's rule twice, you should come up with the same answer. If you know the power series for a function in a limit, it's often faster to just shove in the power series and simplify than it is to do L'Hopital's rule. Especially for something like a square root where the derivatives get a little bit messy, right? Okay. So I thought that might be an interesting thing to see. And all right, my chat is still silent, so I'll continue. Integrals are next. Okay, so we already did an example like this in the warm-up. Okay, you can integrate term by term. You can also differentiate term by term. We did cover that in the power series section. And when you integrate or differentiate, meaning like if you take an antiderivative or a derivative, the radius of convergence stays the same. So if you know the radius of convergence for the original power series, you can differentiate, you can integrate, you can sort these things out, right? And so now we know how to make power series, right? So if we wanted to do something like, this integral here, sine x squared over x squared. Well, here's the thing. That's not going to be so easy to actually do using techniques of integration, right? Maybe we can do integration by parts, but it might be a bit tricky, I think. I think it's going to be a bit tricky to figure that out. Substitution is not going to help, right? Because you substitute the x squared and the 2x isn't there. So what you can do with this is you say, well, look, I need to integrate sine x squared over x squared. And so the first thing I do is I say sine of x squared over x squared. Well, that's 1 over x squared times. So I read out the power series for sine. N equals 0 to infinity minus 1 to the n x to the 2n plus 1 2n plus 1 factorial. Oh, but I need not x, I need x squared. So I need to double my exponent. X squared to the 2n plus 1 is x to the 4n plus 2. Okay, so dividing by x squared, well, to divide by x squared, I just have to subtract 2 from the power. So I get the sum, n going from 0 to infinity, minus 1 to the n, x to the 4n, 2n plus 1 factorial. Now we can integrate. So the integral from 0 to 1, sine x squared over x squared dx. So I just have to do the integral from 0 to 1 of x to the 4n, right? Let me just kind of throw that up in a spot where I have room. Integral from 0 to 1, x to the 4n dx. Well, that's just going to be x to the 4n plus 1 over 4n plus 1. From 0 to 1, well, it's just 1 over 4n plus 1. Okay? So what we get, we just do the integral, right? So the integral of x to the 4n, doing like this, just becomes 1 over 4n plus 1. So we get the sum, n going from 0 to infinity, minus 1 to the n, over 2n plus 1 factorial times 4n plus 1. Okay? So that series, and again, do I know what it adds up to? I don't. But I know that the value is equal to the integral, right? So I have the answer. I have the answer as a series. Oh, missed a question from Sarah. Oh, but she answered it. Let me know if you want me to jump back, right? That's from the previous slide, I think. I was focused on this one. Okay, so we've got that. And so we notice there's a follow-up question here, right? what is the error in the approximation if you use the first 5 terms? Well, the important thing here is to notice that the series we have, because of the minus 1 to the n, it's an alternating series. And so if you go back and you look at the section on alternating series, there's this alternating series approximation theorem, which says that if you want to know what the error is in using the fifth partial sum, you just go to the next term, right? So the next term in the series, right, we go basically to A6, ignoring the minus 1 to the n part. So A6 would be, well, I guess first 5 terms. Maybe if we count 0 as the first term, then I should be just doing A5. Okay, we have language ambiguity, whatever. We get, so 6 plus 1, 2 times 6, 12 plus 1, I get 1 over 13 factorial times 25. 1 over 13 factorial is a pretty big number, right? This is pretty tiny. I could pull out my, let me, on my other, I've got another computer open here. I'm going to grab a calculator, see what we get. Okay, 13 factorial. Okay, and we're going to multiply by 25. Okay, this is 1 over 155, 6, 7, 5, 5, 2, and 4 zeros. It's a pretty tiny error, right? We probably could have stopped after like the second or third term if we wanted to be accurate to like 3 decimal places. I don't think we needed to go quite that far. But it's fun that we can play these games, right? This is typically where you're looking to do approximations. You can also get error estimates using that Lagrange formula from the remainder, for the remainder, right? That one coming, if we go all the way back to here, right? We can go and we can say, okay, I want to use this remainder formula. But then it gets kind of messy because, well, that gives you the error in using the Taylor series to approximate, but doesn't really say much about what happens once you do the integral. So sometimes you can use that remainder formula, but most of the time, if you're approximating, you're using essentially like alternating series approximation formula, because that's easy to work with, right? That's as far as approximations go for sequences in series. I'll stick to that one. There are some other ones there. They're in the book. I guess I'm giving you a take-home, so I could make you go look the other ones up. But chances are, if there's an approximation question, I'm expecting you to use the alternating series approximation theorem to figure that out. Okay. All right. Sarah, I hope you figured out your 6. Where was that 6? Oh, this one here, right? Maybe? I've lost the 6. All right. Let me know. If we're doing okay, I'm going to jump. Yeah, good. Oh, yeah, let's go. Okay. Next slide. Yeah, examples by request. So I went down to Piazza. I don't know if anyone stuck some more up there while I was... let me see. No, there's nothing new on Piazza. So I'm going to use the ones that I gathered into my slides last night. If you've got some that you want to see, let me know. How much time do we have? We don't have that much time left. I'll go a few minutes over time. After all, we used to do 75 minutes for these. You can all disappear if you need to. All right. One request I got. Oh, big P. That should be a big P. There was a WebWork problem like this, asking about a logistic population model. And part of the question asked, okay, find the values of P for which the population is increasing or decreasing. And that's actually pretty straightforward. It just comes down to the fact that if you do a sign diagram for P prime, right? Think back to like Calc 1, right? sign diagram for the derivative tells you where your function is increasing or decreasing. And the derivative depends only on p, right? The derivative doesn't depend directly on t, right? Indirectly, yes, because p is a function of t. But that means that you just have to say, well, look, there are two zeros. There are two critical points, 0 and 93. And I've got something which is going to be positive here and negative out there, right? So that means that it's increasing if 0 is between p and 93. It's decreasing for p bigger than 93. And we don't really consider what happens when p is less than 0 because that's a negative population and that doesn't really make sense, right? So there was actually very little work in answering the first part of that way-work problem. And then the next part, I think, asked for, okay, it said, okay, given some initial value, given p of 0 is, say, 48, like I have here, find the value of t at some later time, like p of 50, let's say. Well, really, that's asking you to solve the differential equation, right? So how do I solve this? It's not linear, but it is separable. So if I wanted to solve this differential equation, I would have to go and say, okay, well, I have 1 over p times 93 minus p. And you know what? I might even, just to simplify, let's put the 500 over here. And then I have, oh, don't forget my dp, 3 dt, right? So I can separate the equation. Multiply by 500, divide by the p times 93 minus p, multiply up by dt. Now, for this one, remember that the way you tackle something like this is with partial fractions. So we're looking for a over p, b over 93 minus p, and we want that to be equal to 500 over p times 93 minus p. So if you get a common denominator on the left and you equate the numerators, we have a times 93 minus p plus b times p equal to 500. So if we plug in p equal to 0, b goes away, we get 93 times a, so a is just going to be 500 over 93. If we plug in p is equal to 93, I get 93b equals 500, so b is also 500 over 93. Okay, well, that was easy enough. So then you would probably want to put that in, right? And again, maybe you want to decide where do you want to put those. So we have this, right? We have 500 over 93 times 1 over p, 1 over 93 minus p is equal to 3 dt. Maybe you want to put those constants on the other side just to make it easier to do the integral. So when you integrate on the left, you're going to get natural logs, right? So you're going to get natural log of p minus natural log of 93 minus p. The minus sign comes in because we have a minus sign here, right? So chain rule gives us that minus sign. And I'm going to put what's 3 times 93? Oops. Didn't want the highlighter there. 279. So I have like 279 over 500 times t plus c. And from here, it's basically messing around with logarithms, right? So we can get the value of c because we can put in p of 0 is equal to 48, right? So at t is equal to 0, I get log 48 minus log of, so what's 93 minus 48? 45 is equal to c, right? So c is the natural log of 48 over, 45. So I'll check in with all you, see if it's alright if I leave it here. We plug in that value of c, and then the remaining work is essentially solving for p, which is a bit of a pain. It's algebra, right? We do log properties. I'll squeeze a little bit in up here. You would get log of p over 93 minus p is equal to this 279 over 500t plus this other log 48 over 45. You take e of both sides, so you get p in terms of an exponential, but then there's still some algebra to kind of rearrange and solve for p. But it's just algebra. Okay. So that's all the work I can fit on the slide, and I want to move on because we've been at this live stream for an hour, and probably I'm not the only one that wants to go start making lunch. Okay, I'll give it a second, see if anyone wants to chime in the comments. Wait until we're caught up. I think we're okay. Okay. I was asked to do a rate in, rate out. Here's one of the ones that I had in my slides before that we didn't have time for. So let's set this one up. We have a tank of water. Okay. It's being pumped out at 3 liters per minute. And we've got some stuff coming in at 2 liters per minute. Let's see, water should be blue, right? Oh, maybe it's toxic substance. So there's toxic stuff coming in. It's green. Okay. So we have okay, that 20, that is a typo. That T there. I think. We could leave it in. Let's leave it. Let's do a constant. And we could do varying concentration if we wanted to. That might make things more exciting. But we already have something that is varying, right? We've got the volume. So volume at 0 is 10. Okay? And now, what is the volume as a function of t? Every minute that goes by, we're pumping 2 liters in and we're taking 3 liters out. So that means we lose a liter every minute. So the volume is 10 minus t. So you want to account for that, right? So now we'll do x. So x of t will be the amount of the substance. Okay, and so we got to set up our differential equation, dx dt. So rate in, so the rate at which things are coming in is going to be the concentration coming in, so 20 grams per liter times 2 liters per minute. Okay, and we subtract off the rate out. So the concentration going out is going to be x over v times 3 liters per minute. Okay, so that is, ignoring units, we have 40 minus 3x over 10 minus t. Okay, or in other words, we have dx dt plus 1 over 10 minus t, actually 3 over 10 minus t times x is 40. And I've written it like that because this is my p of t that I use to get my integrating factor, right? So the integrating factor, I'll do it up here, will be e to the integral of 3 over 10 minus t. Okay, so that is e to the minus 3 log of 10 minus t. And remember, we can bring that minus 3 up. So this minus 3 goes up into the exponent. We have 10 minus t to the power minus 3. E to the log cancels out, and we get 1 over 10 minus t cubed. Okay? I'm going to leave you to finish this off, but we put the integrating factor in, right? So on one side we've got d dt of 1 over 10 minus t cubed times x. And always multiply out that product. Make sure that you actually get the thing you're supposed to get. Should be equal to 40 over 10 minus t cubed. Okay, so we integrate both sides. It's simple power rule on the right hand side to do the antiderivative, and then to solve for x, you got to multiply by both sides by that 10 minus t cubed. Now don't forget that when you take the antiderivative, you're going to get a plus c, right, on the right hand side. There's going to be a plus c over here, and the way you get the value for c is you come up to the initial condition. The initial condition, you have to go back and reread the question. It's here, clean water. Clean water means that x of 0 is 0. We start with no toxic substance, right? There's one other kind of key word here, half empty. Okay, they want the how many grams are in the tank when the tank is half empty. Well, what does half empty mean? We start with the volume of 10. We lose 1 liter per minute. So this half empty is really telling me that I want the concentration when t is equal to 5. Okay, so the rest is just do the integral, apply the initial condition, plug in t is equal to 5. You've got your answer. Okay, I've got one more slide for you. Anything that you still have questions on, of course, you can always hit me on the forum later on. Ari is trying to answer questions there now too, so we'll both do our best. I was asked to do a couple convergence tests for you. Okay, so how do we decide if a series converges? Well, remember, convergence tests, we've got integral test, we've got comparison, we've got ratio, we've got root. Alternating series test. Integral test typically does not come up. The only time where you would do the integral test is if you're looking at something like this and you're like, what am I going to compare that to? I'm not really sure. And maybe you recognize that if I was doing this integral, x over e to the x squared, I actually know how to do that integral. Okay? Because I can rewrite this as the integral from 0 to x infinity, x e to the minus x squared dx, right? And so for the antiderivative, I'm doing x e to the minus x squared. What am I going to do? I'm going to let u equal to minus x squared. du is minus 2x dx. And so I get minus 1/2 integral e to the u du, right? And so I get, okay, I'm going to do bad notation because I don't have that much room. We really should write this as a limit. But what we really have is this. We have minus 1/2 e to the minus x squared from 0 to infinity, right? You're not supposed to use this notation. Maybe I've used it, so now I have to forgive you. You use it, but you're supposed to write a limit, right? Limit as, x goes to infinity for that upper limit. And of course, e to the minus x squared, as x goes to infinity, that's going to go to 0. Lower limit is just e to the 1, so I actually get a value of 1/2, right? So I can do the improper integral directly, and I can get the value. That's when you want to use the integral test, is when you recognize that you have a function where you know how to do the integral, and you can get an answer. That's the right time to do integral test. Now, moving on to something like the second one, you got to decide, converge or diverge, right? Because you see there's this piece and there's this piece. If you think diverge, you should try to compare to the 3n because that's harmonic and it diverges. If you think converge, probably you go with the 2 to the n because we get convergent geometric, right? Well, the point here is that 1 over 2 to the n plus 3n is always going to be less than just 1 over 2 to the n because adding 3n makes the denominator bigger, makes the whole thing smaller. And so all you do for something like that is you'd say, hey, the terms in my series, they're all smaller than 1 over 2 to the n. I know that the sum for 1 over 2 to the n converges, right? It's geometric with r less than 1. And so this series converges by comparison, right? For this one here, we say for large n, the terms are roughly n squared over square root n cubed, which is n to the 1/2. Well, actually, there's 2 ways you can tackle this. Test for divergence is 1. If you take the limit of the terms, the limit of these actually goes to infinity because the degree is higher in the numerator, right? So the terms don't go to 0. If the terms don't go to 0, fails the test for divergence, done. Or you do limit comparison, and the thing you would compare with is n to the 1/2, right? If you take the ratio of this over that ratio is going to be 1 in the limit, and so either both series converge or both diverge. We know that the series with just root n in it, that definitely diverges, so it diverges. The last one I was asked to do, there was one like this in the homework. Actually, I took this straight out of WebWork. The way you want to do something like this is you actually want to try splitting it up. If you have more than one term in the numerator, try splitting it up like this. Okay, do two pieces, and for each piece, I would say, so here I would compare to 7 to the k over k factorial. Because adding 5 makes the denominator a little bit smaller, or makes the denominator bigger, makes the thing smaller, right? So these terms are smaller than 7 to the k over k factorial. And the way you would deal with this, how do you show that that term converges? And it does converge. You would use the ratio test, okay? And for this one, you're going to compare to just k over k factorial, which is simply 1 over k minus 1 factorial. And again, you can, if it's not obvious to you that that converges, and it does, the ratio test is going to confirm it, right? Your ratio is going to go to 0 in the limit, so you definitely it works out. Okay. So ratio test applied to each of those things that you want to compare to is going to show that the series with these terms here, the series with these terms converges, the series with these terms converges, and so each piece separately converges by comparison, and if two series converge, their sum also converges, and that's how you show that that one converges. Alright, I'm at the end of my slides. I'm going to stick here for like maybe 30 more seconds in case somebody wants to chime in with one last question before I go. Otherwise, we're going to end the stream here, and you can watch this later. If you missed anything, it's going to be up on YouTube. I hope it's going to be up on YouTube. There's always a chance that I screwed up, but I'm pretty sure it's going to be up. Alright, so I'm watching that chat window. I'm going to take my computer out of tablet mode, put the keyboard back on so I can stop the stream. See how we're doing. Still no questions? Office hours. I'm working on office hours. If you have times that work good for you, let me know. And here, I'll let me just ask on the chat. I want to know. Lots of people are doing Zoom, so you can actually, like, I guess you video call in and we chat face to face. Oh yeah, and Hannah's got a question. You can use the textbook. Yeah. Tests are open book. I'm not that concerned about listing sources. I mean, to some extent you can. Like if you, let's say you use an integral calculator or something, like you can decide that you don't want to bother doing, especially if you're doing like integral tests, for example. If you want to use Wolfram alpha to evaluate the integral, you can just say, hey, Wolfram alpha. Yeah. And I don't think I want to make you all wait in line, Jared. I'll try to deal with everyone at once. We're gonna go with Piazza. I'm trying to get on there and answer questions every moment that I get. It look like afternoon is popular. I still have to coordinate with my wife to figure out what times she needs to be working. And yeah, we'll try to figure this out over the weekend, and starting Monday, we'll try to be relatively normal. I'll definitely be available over the weekend if you're working on that test and you have questions. And I'll send an email on this as well. But I've turned on private messaging on Piazza. So the private messages, if you want to ask about the test, but you don't want to put your answer up on the forum because then you're giving it away to other people, you can send private messages because then I can still at least do math. I'll try to figure out those office hours for you. And yeah, we'll see how this goes. All right. I'm going to pause for just a second. See how this goes. And I'll try to survey you on this time, see if there's a better time. Again, limited because I've got to coordinate with my wife on things. Oh yes, and the midterm tonight, I hope. Or I will get it up as soon as I can get it up. All right. Yeah, I'm going to stop here, I think. If we open the exam on Thursday, it's not time. Yeah. It's a take-home exam. So you have from when it goes up until the deadline to finish the problems and submit them on Crowdmark. If you've got things going on that interfere with getting it done, let's say over the weekend, if you need more time, like if Monday's not a fair deadline and you want Tuesday, you just email me on that and we'll try to sort something out. Okay, I'm going to figure out how to get out of full screen here. I'm going to stop my recording. Thanks everyone for tuning in.